We have to discuss symmetry elements and symmetry operations in the present discussion. The definition of symmetry operation is given below. The symmetry operation is a movement of a body such that the body appears the same as before even after the move. For example, 180-degree rotation of water molecule is taken for our consideration. Even after the 180-degree rotation, the same water molecule structure is arrived. Here H1 and H2 are two hydrogen atoms. An axis is passing through the oxygen. If a rotation is made through this axis, the two hydrogen atoms are interchanged in their positions. However, there is no change in the structure of the molecule. The same water molecule is arrived. This is called the rotation symmetry. This operation is called a symmetrical operation. Then the definition of symmetry element is given below. The symmetrical element is a geometrical entity about which a symmetry operation is carried out. The symmetrical element may be a point, axis or plane. In general, there are 5 fundamental symmetric operations. They are identity operation, rotation, reflection, inversion and improper rotation. If you think about the first operation, that is identity operation, here the symmetry element is identity element. The identity operation is doing nothing to the thing. See this equilateral triangle. If it is subject for symmetry operation, the same structure is obtained with the specifications A, B and C. All objects have an identity element. An object having no symmetry element other than identity element is called asymmetric. Then next symmetric operation is proper rotation. A proper rotation describes the simple rotation operation of an object about an axis. Then the rotation angle is 360 degree divided by n. C suffix n is equal to 360 degree divided by n. N specifies order of rotation. If you say C2 rotation, the C2 rotation means rotation of the object through an angle of 180 degrees. If you put n here, 360 by 2 is 180. So C2 is 180 degree. For example, consider rotation of rectangle. The rectangle has rotational symmetry of order 2. What does it mean? This is because on 360 degrees rotation, the rectangle attains its original position twice. See, this is a rectangle. After 90 degree of rotation, this is a new position. After 180 degree, the original structure is arrived. After 270 degree, this is the position. After 360 degree, once again we have had the original structure. So during the 360 degree rotation, at 2 times we can get the same structure. So that we are calling this rotation as C2. Next symmetrical operation is reflection. Reflection symmetry is a type of symmetry obtained through reflections. Consider a line that divides a figure into 2 halves such that one half is the mirror image of the other. This is known as reflection symmetry. See here, this is a rectangle. 2 lines are present. This is line 1, this is line 2. Suppose the reflection is made about this line, you can get the original structure. If you make the reflection through this line, once again you can get the original structure. So this is called as reflection symmetry. Then this is inversion symmetry. This is related to parity operator, that is inversion of coordinates x, y, z into minus x minus y minus z. See that consider SF6 molecule. Here 6 fluorine atoms are present. The center atom is sulfur. Keeping this sulfur, if you perform inversion of these two fluorine atoms, then this is F3, this is F6. If you carry out the operation for all the fluorine atoms with respect to S, the same structure is once again arrived. Even after the inversion process of the fluorine atoms with respect to sulfur, there is no structure there is no change in the structure of SF6 molecule. Now read out this statement. Each atom of the molecule is moved to a point at an equal distance from the center of inversion along a line passing through the inversion center. See here, the distance of F6 is equal to the distance of F3 from sulfur. During the inversion process, these two atoms are interchanging their position. This is F3, this is F6. The same condition is true for all other cases. This is F2, this is F5. Even after the inversion operation, there is no change in the structure of SF6. So this is called as inversion symmetry. The final one, symmetrical operation, is improper rotation. Rotation about an axis through 360 by n degrees followed by reflection through a plane perpendicular to rotation axis will provide improper rotation symmetry. That means rotation followed by reflection will provide the same structure. Say S4 operation of methane is the example of improper rotation. Here the methane is having tetrahedral structure that is subjected for C4 rotation, that is 90-degree rotation. We can get this structure. If reflection is made through a plane perpendicular to the rotation axis, once again we can get the original structure of the methane. So here is a summary of the above discussion. These are all the symmetry elements. These are all the symmetrical operations corresponding to the elements. If the symmetry element is plane, the symmetrical operation is reflection in the plane. Suppose the symmetry element is center of symmetry or center of inversion, the corresponding operation is inversion of all atoms through the center. Suppose the symmetry element is proper axis, the corresponding operation is one or more rotations about the axis. Suppose the symmetry element is improper axis, the symmetry operation is rotation followed by reflection. In order to get the same structure, we have to carry out these operations with respect to these elements.